feedback. All right, it is March the 20th, and I've asked you for the feedback about mini project number 1. Do you have any questions related to the lesson in D2L is called random variables. We primarily were talking about probability distributions. We talked about the discrete, which covered the generic or the general discrete probability distribution and the binomial. And then we also talked about continuous probability distributions last Wednesday, which covered uniform and exponential. And the quiz for that was due last night. I haven't looked to see who's done it or anything like that, but do you have questions about any of those topics before we continue on?
I don't know if maybe that I can ask about the quiz.
Is there one you want to ask about?
Yes.
Okay, I can pull the quiz up. Do you remember which question it was?
I know I missed one. I forgot the question. I did write it down. I just forgot.
Okay, let me
It's
see if I can. I'm going into the preview of the quiz, and maybe based on the question or the scenario, you think you could.
um
The first one's a ballet instructor. That's a generic. Let's see. Let's go to page 2.
yeah, I think I did those ones. I actually I think when I did the work what I did the workout,
Uh-huh.
uh it's just I think one of the answers, I don't know why like it gives a different answer what I gave. Like I like comparing the answer or what I got and the one of the choices on the
Okay.
answer is like it's close.
Okay, let me look and see. I've turned off the share. I can actually go in and look at your quiz. Let me see if I can look at your quiz and tell, Nana.
Okay.
Okay, it looks like
I know I missed one
one
question.
question was related to the uniform distribution that you missed.
I think that was the part 3 one. I know I missed that one.
Okay, so you missed one related to the uniform distribution, and looks like the other one was related to maybe the binomial. No, not the binomial. The generic one, the very first one. But the numbers don't look real close. I'll how about this? I'll try to go in after class today and make some comments on the questions you missed, and then you can go in and look at your feedback.
Okay.
Will that work?
Yeah, I think that'll work.
If need be, I can actually do a little short video and send it directly to you.
Yeah,
Is
okay.
that a good plan?
Yeah. Thank you.
Okay, you're welcome. Anybody else? Share my screen again. All right, today's topic, then, we're actually with quiz number 3 that you took last night. That finishes module number 1. So today we are beginning module 2. And there are, I believe, 3 lessons in module 2. And then you'll have the midterm exam. Okay? That's the first exam that you'll have. So it'll cover the content of module 1 and module 2. Today's topic is going to be normal distribution, which is really a continuation of our discussion of continuous probability distributions. Okay. The normal distribution is probably one of the most used and most useful probability distributions. So I'm going to use the PowerPoint that's available in D2L. Again, let me remind you where those things are. Okay, so today we're beginning Module 2. And the first lesson is the normal distribution. And you have normal probability distribution and its uses. There's only one PowerPoint for this particular lesson. Okay. So that's where we're going to begin. So remember, we talked about probability distributions. We just finished it, but just kind of get us back on track. A probability distribution is going to describe for us what should happen if everything worked the way it was supposed to, based on the probability of a particular event, as opposed to telling us what actually did happen when you performed the experiment. If we were to say flip a coin 100 times, okay, we could record what actually happened. We could record how many times we flipped a head, how many times we flipped a tail. When you're describing what actually happened, remember that's called a frequency distribution. The probability distribution tells us what should happen if everything worked the way it should, and we would expect to get heads half of the time, since there's a 1 in 2 chance of a head, and we would expect to get a tail half of the time. So the probability distribution describes what should probably happen based on the probability of an event. And it's used in business and insurance and other real life situations by assigning probabilities to your possible outcomes. And we talked about that previously. Some examples would be like looking at a scenario analysis, your worst case, your best case, the most likely case, forecasting sales, whether you're talking about cars or carpet or furniture, whatever, but you have sales forecasting, risk evaluations, rates of returns on stocks, whether a stock's going to go up, whether it's going to go down, whether it's going to stay the same, even standardized test scores, lifespans of consumable items. We talked about the consumable items. That was an example of the exponential. How long is a light bulb going to last? How long is a car battery or batteries in your TV remote or whatever going to last? Even birth weights of children are based on probabilities. Heights, how tall are you going to be? That kind of thing. So there's a wide variety of uses of probability distributions, whether they're discrete or continuous. We're going to continue our focus on continuous probability distribution. And this morning, we're going to specifically talk about what's called the normal probability distribution. And again, this is probably one of the most used and most useful probability distributions in all of statistics. Okay, so this one is very important. So a normal distribution has the following important characteristics. First of all, it is continuous. Okay, it is a continuous probability distribution, meaning that the curve is smooth and is all connected with no gaps and breaks. So for example, usually this is what a normal distribution looks like. You would have a horizontal number line, and then you have a curve. And notice how I'm able to draw that entire curve without lifting my pencil. That is one of the clues that it is continuous. And again, it's a smooth curve and it's all connected. There's no gaps, holes, or breaks in the curve. Secondly, it is symmetric, meaning that the left side is a mirror image of the right side. The line, the imaginary line that divides the curve into halves, is the mean. So if I could pick that curve up off the paper and fold it in half, you really couldn't tell the left side from the right side. They are mirror images of each other. To be symmetric, if you go back and think about it being a symmetric distribution, we know that there's only one mode. That mode is the data value that occurs the most and is represented by the peak of the curve. It's also true that for a symmetric distribution, the mean, the median, and the mode are all approximately the same value. But if you'll notice, when I drew this curve and started this example, I indicated to you that the measurement that indicates the center or the middle is the mean. Of those three measures, we use the mean. Now, the mean, the median, and the mode, again, are all basically the same because it is symmetric, but we label it with the mean. Remember, the mean is the value that uses all of the data values in its calculation. And so of the three, mean, median, and mode, the mean is the most important and the most accurate. So that's why we label it with the mean. Notice how the curve itself has what we call a bell shape, meaning that the majority of the data is in the middle of the distribution. I mean, think about a bell. You know, you kind of have that dome, and then it kind of comes out and curves in. So the normal distribution is bell-shaped, where the majority of your data is in, the center, and you have very few data values on either end. So it tapers off evenly in both directions.
Isn't what's that? The bell shape a little similar to the histogram? Because I think no breaks, no gaps.
The normal distribution can be overlaid on top of a histogram. Okay, a histogram is a version of a bar graph where it is continuous, all connected, and so forth. But the normal distribution itself is actually a curve. It's not a set of bars. But you'll often see, remember we talked about how to identify whether a histogram was skewed left, skewed right, or symmetric. And
Yeah.
when I'm envisioning symmetric, I'm envisioning something like the curve that I have drawn here on this slide, because symmetric usually implies that most of your data is clumped together in the center and you have very few on the ends.
Okay.
I'll show it to you in just a minute,
Okay.
because I have that on a couple slides over.
All right. Okay.
Okay, so a normal distribution is continuous, it's symmetric, and it's bell-shaped. The
Yes.
shape of that curve will always be continuous, symmetric, and bell-shaped. But it can have different bell shapes. And the shape is determined by two different population parameters. There's two measurements that affect the shape of your normal distribution. They are the population mean, and the population standard deviation. In terms of the population mean can be, let's see, gotta get down here, can be any number that you can think of within our number system, we could select or could have as the population mean. For the population standard deviation, again, we can choose any number except 0. So if I can choose any number for the population mean and any number for the population standard deviation except 0 in any combination, guys, that means there are an infinite number of normal distributions. And I have a picture on the next slide that kind of gives you that idea. Okay, you have the green curve. It's still continuous. It's still symmetric. And it's still bell-shaped. Now it's a skinny bell and kind of a really tall bell, but it still has that bell shape. It is a normal distribution. The red curve, again, you have the bell shape. It's continuous. And it is symmetric about the mean. Again, you know, it's not as tall or skinny. It's kind of more what I would call, I don't want to use the word normal, but it looks like a typical bell. And then you have the blue curve, and the blue curve is kind of short and fat. Okay, so you've got, you know, it's a bell that's kind of short and flat, but it's still continuous, it's still symmetric, and it's still bell-shaped. Again, if you want to think about it being symmetric, imagine a line drawn through the middle of the curve, and the fact that you could fold that curve. I could fold the green curve in half, and I couldn't tell the left side from the right side. I can fold the red curve in half, and I can't tell the left from the right. Same thing with the blue curve. So there's at least 3 right there. But again, I can choose any value that I can think of for the mean, and any value I can think of for the standard deviation except 0. So guys, there are an infinite number of probability distributions. Okay, continue on with the characteristics. And this one's a little weird. You have to go back and think about your probability rules. Okay. This one says the total area under a normal distribution is equal to 1 or 100%. Okay, so what we're talking about when you're talking about this 100% is if you think about the curve, okay, you have your horizontal number line, and then you have that bell-shaped, continuous, symmetric distribution. The area is the region between that horizontal number line and the curve itself. Okay, that's what we mean by the area under the curve. It is the space between the horizontal number line and that bell-shaped curve. Now, this is one of those things where you're going to have to kind of trust Miss Ralston, because to prove to you that it's 1, it requires you to do calculus, because it does seem weird, because no matter how far out this curve goes to the left or to the right, it never actually touches or crosses this horizontal number line. Now I can get really close to it. And if you look at the two diagrams that I have here at the bottom of the slide, it does almost look like that they touch, but they never actually touch. And so that seems a little weird. Okay, but again, we could prove it with calculus, but I'm not going to do calculus for you this morning. But this rule, or this idea that the area, that space under the curve is equal to 1, relates back to the probability property that, remember, if we add up all of the probabilities, all of the things that could happen, it has to total to 1 or 100%. Like with when we talk about the heads or tails, okay? You would have heads, there's a 50% chance, and tails, there's a 50% chance. If you add, that's the only two things that can happen when you flip a coin. When you add those together, they total to 1. We're beginning to think about relating, and I showed this to you the other day with the uniform. Again, that probability corresponds to the area under the curve. And we saw that with the uniform distribution, that rectangular shape. We're just now going to apply it to a curve. And there's a little couple of nuances because the curve technically never touches the x-axis. There is a shorthand notation that's sometimes used, so you may want to be familiar with that. It says if x is a quantity to be measured that has a normal distribution with a mean mu and a standard deviation sigma, we write it this way. This is the shorthand notation that you might see when you're reading reports, or you could use when you're writing reports. This says that the variable x approximates a normal distribution. The letter N stands for normal, with a population mean, which is represented by the Greek letter mu, and a population standard deviation of sigma. And again, it's just a shorthand way to write it instead of having to write it out in words. Okay, so let's look at some of the uses. Again, there are lots and lots of uses. And so I want to show some of those to you. The height of a population. Most people in a specific population are of what we would call average height. That's kind of like middle of your curve. So most of your people are going to be average. That's your mean or average. And within a population, as you move away from that middle, okay, remember that's your middle. So you got to look at, this is going to be, think about this curve. It goes short to tall. And we don't have very many people within the population that are really short or really tall. The stock market. Okay. Again, notice here, Nana, this, they start out graphing it using bars and making a histogram, but then they've overlaid the normal distribution on top of it. So again, that's kind of the idea. You can actually have a histogram and then think about whether that histogram is a normal distribution, which would typically be symmetric and have that bell shape. But again, that gives you an approximation of the stock market and what you would expect to make on a particular stock at a particular time.
Okay, thank
Um,
you.
this graph has multiple normal distributions, and it's comparing the income of a country over a period of time. The wages of the middle class population makes the mean. So you got your middle class, and you can work out from there. And it shows it over a period of time. So you have different curves for different years. Birth weight of babies. Again, here you can see they used the histogram, but then they overlaid the normal distribution. Again, most babies are going to be of what we would call average weight. You occasionally have those babies that are born that we would call premature, and so their weights are really low. Occasionally, you have someone who has a baby who is unusually, I don't know if large is the right word, or unusually heavy. These measurements are in grams, okay, which is not a familiar measurement scale for us. But I know in, say, in pediatrics, I know when we would take my daughter to the pediatrician, at that 1 week checkup, 2 weeks checkup, they would always weigh her and then look at it in relationship to the distribution to see if she was developing normally, or if there perhaps appeared to be some sort of problem. Inventory forecasting. So a company needs to know what materials they have, what do they need, when do they need it, so that they can plan on getting that. Again, this one is in a histogram format, but I can visualize my normal distribution on top of that. Okay, so you may not always see it drawn as a curve. It could be in that histogram format. Blood pressure, diastolic blood pressure is to be normally distributed. Milk production for cows is a normal distribution. Temperature changes, thinking about climate change. Again, this one displays it in terms of different years, and you can see the comparison and how things have changed. Okay, so again, there are lots and lots of uses of the normal probability distribution. And in fact, some of the distributions we've talked about, like the binomial, can be approximated using a normal distribution. The exponential can be approximated using a normal distribution. So even if I don't have access to the information to do a binomial or the information to use an exponential, we can approximate those with a normal distribution. So again, it is one of the most used and most useful distributions. So I want to talk a little bit about the history of the normal distribution. Before we had technology, before we had computers or we had calculators, the only way to solve a problem that involved the normal distribution was basically to do very tedious, very complicated calculations using a crazy looking formula. Okay. And the formula for a normal distribution is kind of here in the middle of this slide. Okay. Remember from algebra, we typically had an equation that would represent the shape of a function. For example, if we had f of x equals x squared, hopefully you remember that that particular shape would be a parabola. Well, the equation for your lovely, continuous, bell-shaped, symmetrical distribution, which we call the normal distribution, is this crazy looking thing here in the middle. It's a fraction. It's really hard to see in the way it's typed there, but it's really e raised to the negative x minus the mean squared divided by 2 times the standard deviation squared, all over standard deviation times the square root of 2 pi. I mean, it's a yucky looking fraction, and the only option we had before we had calculators and computers was to do calculus. So mathematicians realized that not everyone would know how to do calculus or understand how to do calculus. So they decided they would create a standard or a standardized normal distribution so that anybody, the general public or whatever, would have access to the information. And so they wanted to select a value for the population mean and a value for the standard deviation that would make the calculus calculations as simple as possible. And so they selected for the mean, they selected a value of 0. I mean, 0 is easy to calculate with. For the standard deviation, though, they couldn't use a value of 0. The reason they couldn't use the value of 0 is, notice that this value of this population standard deviation is in the denominator of the fraction. And because it's in the denominator of the fraction, it couldn't be 0. Because we know from basic math that you cannot have 0 in the denominator of a fraction. So the next best number was 1. So the standard normal distribution, you had probably a group of mathematicians working to do the calculus, and they created tables that someone could use to work a problem that involved a normal distribution without doing calculus. And I hope this link works. It'll take us out. Nope, it didn't take me where I wanted to go. Okay, but we can look at a normal distribution table. I want to show you what they look like. So they created these tables. Okay. I don't want to watch it. I don't want to watch it.
Hi guys, in this video.
Okay, but you had your z-score and they had the numbers across the top, and you had to know how to read it. Well, the problem is, and this is the way Miss Ralston learned it, was you had to understand how this table was set up. This particular table is set up so that we read from the center, which was the mean, out to the value of interest. But if I looked at a different table, for example, if I go over here and look at this one, this particular table reads from all the way from the left-hand side up to the z value. And so depending upon which textbook you picked up, which maybe researcher you were working with, you had the tables were set up differently. So you had to know how to read it. You also had to be familiar with how to convert from, I'm sorry, I got off on the wrong thing. You had to convert from the traditional scale to this normal scale using the Z, which we talked about earlier in the semester. The Z you would take your value of interest minus the mean and divide it by the standard deviation. Guys, that was a lot of work. You are so lucky that we're able to use the technology. A TI 8384 calculator will do the calculations if you know how to enter the information. We're going to use Minitab to do the calculations for us. Minitab is programmed. It has, it does all the calculus and stuff behind the scenes. And so it makes it a lot easier. What we focus on then is the interpretation. What does that tell us and how does that help us? Now, I didn't say all this here to scare you, okay? I'm just trying to make sure that you kind of know how, I guess, how easy you have it, because it's a whole lot easier to let Minitab do the work. There are two different ways that these questions are presented, and it's all in the wording. I tend to refer to them as type 1 and type 2. Now, this is Miss Ralston's lingo. It's not the official statistics lingo, okay? But I tend to call them type 1 and type 2 in hopes that you can make a distinction. For type 1, usually the question related to the problem is going to say something like, find the area under the curve that and it's going to tell you something. Find the percentage that. Find the probability that. Okay, these phrases, area under the curve, percentage, and probability, in this context are all synonyms. Okay, in the problem itself, there's information you're going to have to be told. In the scenario, you should be told that your variable is normally distributed. So again, it should be very easy to identify that you need to use the normal distribution. Again, because it is going to say somewhere in the scenario that your distribution or your variable is normally distributed. It should give you the population mean, which is mu. It should give you the population standard deviation, which is sigma, and then it's going to give you the condition. There are really 4 different conditions that you could be asked to calculate or to think about. Okay, so the 4 different conditions, it could be that you're greater than, or any kind of synonym, more than. You could have less than. You could have a between. And then the last one is an or statement. The condition will determine what command or what selections you make in Minitab. It would also affect, if you were using a calculator, what command or options you select. And even if I were doing it by hand using the table, it would make a difference. Okay, so it's important that you know which condition you have. Again, I want to stress to you this idea here is we're relating the probability to the area under the curve. I suggest that you read the scenario that you're given from start to finish. You're going to want to write down your population mean and your population standard deviation that you're given. It will also help you to draw a picture of the scenario, because that's going to help you decide, is it greater than, less than, or so forth. And there's certain words that go with that, and we'll talk about those in just a minute. On this slide, and it is slide number, let me tell you what number it is. It is slide number 12. I have the Minitab instructions for these problems. Okay, this is slide 12, and I have the Minitab instructions. Now remember, we're dealing with probability, or the area under the curve. And we learned a few lessons back that all probabilities are between 0 and 1. So this idea of finding the area under the curve, which corresponds to the probability, I still have to have a positive number. The probability, aka area under the curve, should never, ever be negative. It should also never be ever greater than 1, because we know all probabilities are between 0 and 1. It just amazes me when students put an answer on a question, on a test or a quiz or whatever, that's bigger than 1 related to probability, or they give me a negative number. Guys, that is not mathematically nor statistically possible, because all probabilities should be between 0 and 1. They should never, ever be negative, and they should never, ever be greater than 1. And I believe then we jump into some examples. Okay. And I moved the examples over to a Word document because I need some space to work them. Okay. So we're going to begin looking at the examples. Any questions before I start?
No questions.
Okay, this says, according to the American College Test, results from the 2022 ACT testing found that students had a mean score of 21.524 with a standard deviation of 2.419. Assuming that the scores are normally distributed, find the probability that a randomly selected student has a reading ACT score greater than 26. Okay, so a couple things I want to stress here. It tells us clearly that our ACT scores are normally distributed. So there's no question that this question is about a normal distribution. It also tells us that the mean was 21.54. I want to make a note. The mean is 21.524. And it tells me that the standard deviation is 2.419. Then it says, find the probability that I want to emphasize that we're talking about a randomly selected student has a reading ACT score greater than 26. Okay, so if you're looking at this in symbols, they're asking you what's the probability that the student's score is greater than 26. Now, again, notice this says, find the probability that A. A implies we're only selecting one student. Okay. And I'm pointing that out because on Wednesday, we're going to look at what if we look at the possibility of selecting 5 students or 10 students. How does that affect or change our problem? Okay, so it's important to recognize here that you're selecting one student. Okay, so I'm going to try to draw us a picture of what's going on here. Okay, so I have a normal distribution. So I have my horizontal axis, my bell-shaped curve. The mean is the measure of center, and it's given to me as 21.524. So the value in the middle of the number line, because remember the mean is a measure of center, is 21.524. This becomes your point of reference. The question then asks, what is the probability that a student scores greater than 26? Okay, greater than 26. So 26, if I think about it, 21.524 is in the middle. 26 is going to be somewhere on the right-hand side. I just randomly put it there. To be greater than 26, I'm looking for this area or the region under the curve from 26 to the right. Greater than is to the right. So I'm looking for the area of this red shaded region. Notice that this red shaded region is on the right-hand side of the curve, and it's at the end of the curve. So this is what we would call a right tail. That is the phrasing that Minitab uses for a problem where it involves greater than. Okay, greater than, because again, visually it's on the right-hand side, so it's called a right tail. Okay, so now I'm ready to go out to Minitab to work through my problem. Okay, so I'm in Minitab. We go to graph. Whoops. Has to wake itself back up. Give it just a minute. Okay, so we go to graph, probability distribution plot. Graph, probability distribution plot. I want to view the probability for one curve. Guys, we will only be considering one curve at a time, and we want to view the probability. You have to double click here. Doo-doo. We have to indicate the distribution that we have. It is normal. Now, Minitab does a whole bunch of different ones. We are dealing with a normal distribution. It clearly said in the problem, normally distributed. I have to indicate the mean that was given in the problem. It was 21.524. I have to indicate the standard deviation given in the problem, which was 2.419. 2.419. Excuse me, then I go to options. We have been given a specified X value because the value that they gave us was 26 and it's on the horizontal axis. Let me make you a note here. This is a specified X value. It's what Miss Ralston calls a type 1. Okay, so choose a specified X value. We decided it was a right tail because I'm on the right-hand side, and my value of interest was 26. I click OK. I click OK again. And it gives me this graph, and I'm going to copy the graph over to my paper. Let me get in the right spot here. Okay, so here's the graph, and notice this graph looks very similar to the one that I had hand drawn. Okay. What I need, the answer to the question, is this decimal value that's kind of hanging out in space above that red shaded area. It is 0.03213. Okay, so that is the area of that red shaded region. But what does that tell me in the context of this problem? In the context of this problem, that means a randomly, or let me say it this way. The probability that a randomly selected student has a reading ACT score greater than 26 is 0.03213 or 3.213%. I can take the decimal and convert it to a percentage. If you don't remember how to do that, to go from a percent or a decimal, 0.03213 times 100% gives you the percentage. So scoring greater than 26 on the reading ACT in 2022, you only had about a 3% chance. Not very, it wasn't very likely that you were going to score over 26 or greater than 26. Now, Minitab is doing the work for you. You need to focus on making sure you are selecting the appropriate conditions. Right, next question. It's the same scenario, okay? We have the same scenario. The variable is the reading ACT. It is approximately normal with a mean of 21.524 and a standard deviation of 2.419. Okay, it's the same scenario. I still know the variable is normally distributed. I still know the population mean. I still know the population standard deviation. It says find the probability that a randomly selected student has a reading ACT score less than 21.7, which was Georgia's mean ACT score in 2022. Okay, so again, I'm going to start out. I've identified the fact that it's normal. It told me that in the problem. I've identified the population mean. I've identified the population standard deviation. I'm going to draw a picture. So I have my horizontal axis, my normal bell-shaped curve. The mean is in the middle, which is 21.524. The question here says, what is the probability you are less than 21.7? So my point of interest is 21.7, which is just a little bit more than the mean, and we want to be less than. Less than is to the left. Values that are smaller or less are to the left. So I'm looking for this area or this red shaded region. Notice that less than is on the left. This is referred to as a left tail because your region is on the left because it's less than. So again, I have my picture. I have all the information. I'm going out to Minitab. Okay, we go through the process again. Graph, probability distribution plot, one curve. We view the probability, clicking twice. Doo-doo. It is a normal distribution. Our mean for this problem is still 21.524. The standard deviation is 2.419. I go to options. Again, I have a specified X value on the horizontal number line. It is a left tail this time, so I select left tail, and my point of interest was 21.7. I click OK. OK. And again, I'm going to copy it over here to my paper so we can see it. Okay. So again, what you're looking for is this decimal value that's kind of hanging out in space above that red shaded region. So the area of this red shaded region is 0.5290, and that would be your answer. Now, I know for the test questions on your quiz and the questions on the midterm, that's what you're going to enter, 0.5290. Again, it's important. D2L wants you to put that leading zero. Again, what that tells us in the context of this problem is that the probability a randomly selected student has a reading ACT score less than 21.7 is 0.5290 or 52.9%. Typically, so you'll know the difference, typically if the question asks you for a probability, you're going to put the answer in decimal form. The other word you could see is it could ask for a percentage. And if it asks for a percentage, that's when you want to write it in that percent form. Okay, so the question itself will tell you which format to put the answer in. Okay, next question. It's the same scenario. Okay, we have the reading ACT scores are normally distributed with a mean of 21.524, a standard deviation of 2.419. Okay, same scenario we've been looking at. We haven't changed it. The question says, find the probability that a randomly selected student has a reading ACT score between 18 and 24. Okay, between 18 and 24. So again, let's see if I can draw a picture. Hold on just a second. I got something on my glasses. Okay, so I'm going to draw a picture. We have our horizontal number line, our bell-shaped normal distribution. The mean is in the middle, 21.524. I want to be between 18, which is going to be on the left, and 24. And I want to be between that. So I'm looking for this region kind of in the middle of the curve. Okay, that is in between those two values that I'm given. Minitab refers to this as the middle. If you think about it, it kind of makes sense because we're in the middle of the curve. Now I'm ready to go out to Minitab to do my calculations. Graph, probability distribution plot, view probability. It's normal. Mean is 21.524. Standard deviation is 2.419. Options. Again, I have a specified X value. We're in the middle. And you have to enter the two values. Guys, you always enter the smallest value first and the largest value second. Okay, so we go from 18 to 24. The smallest value is entered first as value 1. The larger value is entered second as value 2. I click OK. OK. And again, we get the picture. And again, what you're looking for is this decimal value that's kind of hanging out in space above that red shaded region. So for this problem, my answer is 0.7744. Now, again, in terms of what does that tell us, what that tells us is that the probability a randomly selected student scores between 18 and 24 on the reading ACT is 0.7744 or 77.44%. Okay, let's do another one. This one's a little bit different. Okay, this one I want to stress is a special case. It's the or. Minitab does not calculate this directly. Okay, there's not a single command that will do the or at one time. Okay, this one is a special case. You have to do a little bit of extra work. We still know that our variable, the reading ACT scores, are approximately normal with a mean of 21.524 and a standard deviation of 2.419. It's the same scenario that we've been looking at. It says find the probability that a randomly selected student has a score that is less than 20 or greater than 23. We have kind of an option here. Did they score maybe low or did they score high? It has an or. Let's draw a picture so you can see it visually. You have your normal bell-shaped continuous distribution. The mean is in the middle, which is 21.524. Remember, that's given in the problem. This one says, what is the probability you're less than 20? Okay, the fact that that is a less than, so your less than is a left tail, or it's greater than 23. So notice you have two options here. Okay, this is a right tail. Greater than is a right tail. So it's kind of like you've combined a left tail and a right tail together. Mathematically, the word or means to add. So in this case, we want to figure the left tail plus the right tail to get our answer. But Minitab will not do that directly. I have to do the left tail as one calculation. I have to do the right tail as a second calculation. And then finally, to get my final answer, I have to add the left tail and the right tail together. There's more steps here. Okay. but there's no other way to do it unless you want to do some calculus, and I'm probably sure that you do not. Okay, so I'm going out to Minitab, and I'm going to calculate the left tail first. It does not matter which one I do first. I just tend to work left to right. So I have graph, probability distribution plot, view probability. It is normal. My mean is 21.524, standard deviation of 2.419. That was given. My options. I'm doing a left tail, and we wanted to be less than, what was it, 20? Let me make sure. Whoops. Less than 20. Okay, so my point of interest for the left tail is 20. And I click OK. And OK. I'm going to copy here. Okay, so this graph gives me the left tail. Okay, this is my left tail. And my value for the left tail is 0.2643. So this left tail is 0.2643. Okay, there's my first calculation. But I'm not finished, because it says, or we could be greater than 23, which is a right tail. So now I'm going to figure the right tail. Okay, so we go graph, probability distribution plot, view probability, doo-doo. Everything stays the same. I now have a right tail, and we want it to be greater than 23. And I click OK. And OK. Copy my graph. Okay, so now I have the right tail. This is my right tail. And my value for the right tail is 0.2709. So the right tail is 0.2709. So now I have the left tail and I have the right tail, but I'm still not finished, because to get to my final answer, I've got to add the probability of the left tail plus the probability of the right tail. And to do that, I'm going to use my handheld calculator. Okay, so I would have 0.2643 plus 0.2709. I get 0.5352. Okay, so this tells us there is a 0.5352 probability that a randomly selected student scores less than 20 or greater than 23 on the reading ACT. If you wanted that in percentage form, in terms of a percentage, this would be 53 0.52%. Now that question takes a little bit more effort because of the or. You're just putting two pieces together, a left tail and a right tail. One thing I want to point out, notice on this command, we've used the option for right tail, we've used the option for left tail, and we've used middle. We will not be using the option for equal tails. Questions? Okay, I have several other examples, but I want to move on to the second type. And then if we have time, I'll come back and work through some additional examples. Okay, so let's move on to what Miss Ralston calls type 2. Type 2 is a little bit different. It's what technically is called an inverse normal distribution. Okay, because you start out knowing the probability or the percentage, and you're asked to find the X value. So you're working backwards. You know the probability. So it's sort of like Jeopardy. You know the answer and you got to work your way backwards. Okay, so it's called the inverse normal. Minitab calls this a specified probability. Now, even with these problems, okay, even with these questions, you are still going to be told in the scenario that your variable is normally distributed. You still are going to be told the population mean, which is mu. You're still going to be told the population standard deviation, which is your percentage, and you're going to be given the probability or the percentage. Now, we do have to, when we're dealing with this in Minitab, you will have to convert that probability to decimal form. Probably for some students, the biggest challenge is recognizing whether you have type 1 or type 2, whether you have to find the probability or whether you're finding the X value or your cutoff score. Okay, but guys, it's really in the phrasing and the wording of the question. So you have to take the time to read the scenario fully, carefully, and read every detail. It's not something you can skim through. On slide 20, I believe, I do give you the instructions for Minitab for the inverse normal distribution. Okay, it's still important that you read the scenario, you write down your population mean, your population standard deviation. It will also help you to draw a picture. Okay, but the keystrokes for the inverse normal are on slide 20 of the PowerPoint. So we're going over to the Word document, and let me scroll down a little bit and find the question. Okay, we're still looking at the ACT question, but this time we're looking at it from a different perspective. Okay, it gives us a scenario again. According to the American College Test, results from the 2022 ACT testing found that students had a mean score of 21.524 with a standard deviation of 2.419. Assuming that the scores are normally distributed, find the 80th percentile. So again, in this scenario, they've told us that our variable is normal. They've told us that the population mean is 21.524 and the standard deviation is 2.419. That information really didn't change. What changed is the question. And this question is asking us to find the 80th percentile. Now, you have to remember how to interpret a percentile. That means that 80% of the ACT scores were below the value that you're looking for. Okay, remember percentiles are always the percentage below. And again, that's important to recognize because the fact that they are the percentage below, this would be considered a left tail. Now let's talk about what this would look like visually. Okay, you still have your horizontal number line. You have your normal bell-shaped distribution. The mean is in the middle, which is 21.524. Now, if you think about reading this curve, it goes from 0% on the left up to 100% on the right. The mean, remember, is in the middle, so that's our 50% mark. So the mean divides the curve 50-50. There's 50% below, 50% above. You also can think about it, this goes from low to high. You might see words like bottom to top, okay? But again, you always read left to right, and it always runs low to high. So this says 80% of the scores were below this number that I don't know. Okay, so if I start at the left, I'm at 0%. I get to the mean, I'm at 50%, but I'm looking for 80. So somewhere over here on the right-hand side of the mean is going to be some score. And below that score is my 80%, which is 0.80. Okay, so I already know that this red shaded region is 80%. See, I actually know the answer. I know that this red shaded region is 80%. What I don't know is what score on the ACT that corresponds to. So I'm going out to Minitab. Again, this one's called a specified probability. Okay, so I'm going out to Minitab. Graph, probability distribution plot. It's still one curve, and we want to view the probability. It's a double click. Doo-doo. I have to indicate it's a normal distribution. I have to input the mean. I have to input the standard deviation. I go to options. This is where it changes. I now have a specified probability. That specified probability is in the left tail and is 80%, which is 0.80. I click OK and OK. Now let me show you how to read this graph. Okay, on this graph, notice that the number that's hanging out in space is 0.80. Okay, that verifies that this is 80%. But that's not what I'm looking for. What I'm looking for is the X value that corresponds to. I'm looking for this number on the horizontal axis. Now you've got the 21.52. Don't confuse that. That's the mean. That's the one that's in the middle. Okay, so this is my X value. At the end of this red shaded region is my value, 23.56. Kind of scroll up. Okay, so this value would be 23.56. So if I'm interpreting what this says the 80th percentile of the ACT scores in 2022 is 23.56. So if a student scored 23.56, that would mean they're in the 80th percentile, and that 80% of all the students who took the test scored below 23.56. Okay, let's do another one. We're going to change examples this time. This example says the lengths of pregnancies are normally distributed with a mean of 268 days and a standard deviation of 15 days. If we stipulate that a baby is premature if the length of the pregnancy is in the lowest 4%, find the length that separates premature babies from those who are not premature. Premature babies often require special care, and this result could be helpful to hospital administrators in planning for that care. Okay, so again, guys, notice very clearly, okay, without a lot of guesswork, it tells you that our variable is normally distributed. It tells you the mean, and it tells you the standard deviation. So I know that I have a normal distribution. Tells me that in the problem. I know that the mean is 268 days, and I know that the standard deviation is 15 days. So I know that I've got to work the problem as though it is a normal distribution. It continues on and says that if we stipulate that a baby is premature if the length of the pregnancy is in the lowest 4%. Guys, that word lowest is important. Okay, you can't just overlook it. So let's see what kind of picture we can draw here based on this information. Well, we know it's normally distributed. So we have our horizontal axis, our bell-shaped curve. The mean is in the middle, which is 268. Now, again, I want to remind you, just for emphasis sake, that this runs from 0% to 100%, low to high. So the fact that this says lowest 4%, I hope lowest makes you think we're over here somewhere on the left. Low, lowest, and this red shaded region would be 4% or 0.04. This is lowest because it's on the low end. And we're looking for, again, this value. And again, what that value is going to do in terms of my graph is if babies are born in this red shaded region, they're considered premature. If they're born after that date, they're not premature. And we want to know how many days that corresponds to in terms of the pregnancy. So again, this is lowest. It's important to realize that lowest 4% is going to be a left tail. Low is on the left. So we go graph, probability distribution plot, one curve, view probability. It is normal. My mean this time is 268. My standard deviation was 15. So I adjust those numbers based on what I'm given in the problem. Options, I have a specified probability in the left tail of 4%, which is 0.04. I click OK. I click OK. I copy the graph so that you guys can see it. Okay, again, notice you can kind of double check yourself. Notice that it does indicate the 0.04 or 4% hanging out in space. What you need is this value on the x-axis is 241.7. So, excuse me, 241.7. So basically, if a baby is born prior to about the 242nd day, it will be considered premature. A baby born before the 242nd day of pregnancy would be considered premature. Now, one of the things I will caution you about in terms of your quiz and in terms of the midterm is to pay attention to how they ask you to round. Most of the questions may say round, to the nearest whole number, round to 1 decimal place, or whatever. So just be careful. It doesn't indicate on the examples how to round, but I know that it does on the quiz and on the midterm. So just be careful to read and round appropriately. Questions before we take a look at another one? Okay, the next question says, and it's a totally different scenario, says, men's heights are normally distributed with a mean of 69 inches and a standard deviation of 2.8 inches. The standard casket has an inside length of 78 inches. A manufacturer of caskets wants to reduce production cost by making smaller caskets. What inside length would fit all men except the tallest 1%? Now, here again, notice that it does clearly tell you in the problem that it is normally distributed. It tells you that your mean is 69 inches. It clearly tells you your standard deviation is 2.8 inches. It also tells you this information about a standard casket. Okay, that information is just extra. Okay, it's extra information that, quite honestly, you don't necessarily need to work the problem. It also tells you that the manufacturer wants to reduce production costs and he wants to change it so that his caskets will fit all men except the tallest 1%. Okay, so let's see if we can draw a picture. Okay, so I know that I have a normal distribution. My mean is in the middle, which is 69. Again, thinking about how this curve works, okay, you go from 0% on the left to 100% on the right. In terms of height, we would go from short to tall. And it says he wants to exclude all men, or he wants the casket to fit all men except the tallest 1%. Well, tallest, I hope, makes you think that it's going to be over here somewhere on the right. Okay, tallest 1%. 1% is 0.01. Okay, so we're going to exclude basically men that are like really, 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 really tall. Okay, it's important that you think about where that's going to be, because the fact that this is tallest and we're on the right indicates that this would be a right tail. So again, I'm going out to Minitab to do the calculation. Graph, probability distribution plot, view probability, It is normal. My mean was given as 69. The standard deviation was given as 2.8. I have a specified probability on the high end, so it's a right tail. And we're going to basically exclude 1% of men, 0.01. I click OK. I click OK. And we get our graph. And I'm going to copy it over here to the paper. Okay, so again, notice that on this graph, it shows the 0.01% hanging out in the red shaded area. What you're looking for is this value on the horizontal axis, which is 75.51 inches. So the casket maker could make his caskets about 75.5 inches. Okay, so we would say, let me make some space here. The manufacturer could produce caskets with an inside length of 75.51 or 75.5 inches. And he would still be able to fit 99% of the population. I mean, think about it, 75.5 inches, that's 6 foot 3.5 inches. So somebody who was, say, 6'5", 6'6", 6'7", would probably have to special order a casket. Okay, but he would still, I mean, think about it. If he could shorten it from 78 inches to 75.5 inches, you're saving 2.5 inches. And after a while, that's going to add up in terms of your supplies and things needed to produce caskets. So you would save money over an extended period of time. Questions? Okay, do you want to see more examples?
Can I see one more example?
Of which one? Of top 1 or top 2 or both? The ones we're doing now?
Maybe the type 2.
Okay. All right, so I'm going to scroll down to the next question. Okay, the next question says, the cell phone company Samsung wishes to set a minimum hours guarantee on its new model as a high quality cell phone. Tests reveal the mean hours are 67,900 with a standard deviation of 2,050 hours, and that the distribution of hours follows the normal distribution. They want to set the minimum guaranteed hours so that no more than 4% of cell phones will have to be replaced. What minimum guaranteed hours should Samsung announce. Okay. So again, looking through this problem, it tells you that it follows a normal distribution. It tells you the mean. The mean is 67,900 and the standard deviation is 2,050 hours. It also tells you that they don't want to replace no more than 4%. Now that's a little weird phrasing. So stop and think for a minute what the phrase no more than means. No more than is another way to say less than. They just like to use fancy language. No more than is the same as saying less than. Okay, so the fact that this is a less than kind of puts in my mind that it's going to be a left tail, but let's draw us a picture. We know it's a normal distribution, so I have a bell-shaped curve. The mean is in the middle, which is 67,900. It says no more than 4%. Again, thinking about how this curve works, we go from 0% to 100%. Okay. So we don't want to have to replace the phones. Okay. No more than 4% of the cell phones will have to be replaced. Okay. So we want to be less than 4% are going to be replaced. Okay. So less than 4%. Less than, again, makes me think about being on the left. And I have 4% in the tail. So again, this makes me think of a left tail. I'm going out to Minitab. Let me check my numbers. Okay. Graph, probability distribution plot, one curve, view probability. My mean was 67,900. My standard deviation was 2,050. It is normal. Options, it's a left tail, 4%. Oops, I forgot to copy. Sorry. Okay, so again, notice that you have the 4% kind of hanging out above the curve. That's not what you need, but what you need is the number on the horizontal axis, which turns out to be 64,311. So probably to be on the safe side, I would say that the minimum guaranteed hours Samsung would announce would be about, I would approximate it to be about 64,300. Now, the answer you'd put on the test would be 64,311 because that's the answer. But again, you're looking for this minimum guaranteed hours. So they probably would round it. They probably wouldn't announce 64,311. You know, so we would say approximately the phone's going to last 64,300 hours. Nana, you all right?
Yes, I am.
Okay, there's a couple of other examples on the paper. So here's what I would tell you to do is maybe work through those. And then if you're, you don't have the right answers, but if you're struggling with those questions, then maybe that's something you need to come back and ask about on Wednesday.
Okay.
Okay. Or at least work through, maybe work through the homework one time so that if you have questions about the homework, we can revisit that on Wednesday.
Okay.
Emmanuel, do you or Gabriella have questions?
No.
Okay, we are done a little bit early, but I really don't want to get into the next lesson. And we have covered a lot of ground today. So I feel like you could use the time to take a breath. Okay. Yes, ma'am.
Real quick, about the quiz, can I send you my work on your email, like to know,
Yes, if you want to send me, like if you have, like, you can take a picture of it or scan it and send it to me as an email, and then I can maybe see where you're making a mistake
okay,
and
I
help you
will.
help you correct it. Okay, that's fine.
Yes. Okay. Thank you.
You're welcome. Anything else, ladies and
Um,
gentlemen?
I don't think I have any more.
Okay. Well, if
Yeah.
not, then I will plan to see you guys Wednesday morning, and I'll answer any questions you have related to normal distribution, and then we'll pick up with the central limit theorem.
Okay.
All right.
Thank you
Y'all,
for today.
you're welcome. Y'all have a good afternoon.
You too. Bye.
Bye.